Hi, guys. Trying to let people into the classroom from the waiting area. People are still joining. Let's just give it a minute for everybody else to arrive. All right. Okay. So I think I'm just going to go over some administrative stuff really quick. So we're going to finish up chapter 4.3 today, and then we're going to start and hopefully finish chapter 5.2. Okay. So make sure you have your lecture example notes printed out for those chapter sections. It looks like, and I've been thinking, probably what we'll do is I'll cover, hang on just a second. For the test on Thursday, I think the test will cover up to 5.2. So that'll be essentially chapter 3.5 to 5.2 is what we're going to cover on the test. We will try, I'm going to try to get through most of chapter 5.3 tomorrow in the lecture so that we have that. And then, but that won't be on the exam. Okay, so I know I included 5.3 on the homework assignment for this week, but it looks like I'm gonna, I think I'm gonna make 5.3 not due this week for homework, and also not on the exam this week too. So keep that in mind, but we will do 5.3 tomorrow as for lecture stuff, but it won't be on the exam, okay? And then if you guys wanna come to office hours and ask questions on the review, if you can take a look on Blackboard, we have our test 1 review. So I posted a file note up on our main course page that said, you know, for test 1 reviews, these are the questions that you want to take a look at. Because like, remember for test 1 review, we only needed like a certain portion of those. Now for the test 2, we'll go back to the test 1 review sheet because there are some topics on there that you want to look at. So there are questions that you can take a look at for that. Also, if you can, I also created a new folder called Exam 2 Review Extra Materials. And these are test 2 review materials from previous semesters. And it says, like, basically, I think you only need the questions 1 through 4 for those to cover the material that we're going to be getting for our exam. Okay, so if you want to take a look at those, there's solution sets that are posted on with those as well. Those will help you prepare for the exam that's going to happen. That will start, the exam window will start on Thursday afternoon, like we did in the past. So the exam will start on Thursday afternoon, the availability, and then it will go until Friday afternoon, but it'll be essentially 1 whole class period for you to take the exam, okay? The homework for this week is 4.2, 4.3, and 5.2, so only 3 chapter sections, and that'll be due at midnight on Thursday, or by midnight on Thursday. So I think that's about it for administrative stuff. If you guys have questions that you want to go over, old material, test review stuff, or homework problems, or whatnot, excuse me, you can come to office hours and we can talk about it. And then we'll go over all that stuff to help you review for those things. Okay. So with that said, why don't we go back to chapter 4.3. Give me a second. 4.3. Where we started to talk about the normal distribution, right? So our normal distribution is this bell-shaped curve, okay, in chapter 4.3. And it's the most common probability distribution function because data in the natural world tend to sift into this bell-shaped curve on its own, especially when you have a binomial experiment in the background. So binomial experiment, remember, is a success or failure. It's a yes or no type of a question. Does this drug work? Yes or no? Okay, or do you agree with this? Yes or no? Or do you have this? Yes or no? So it's always like a binomial, a yes or no type of a question that needs to be answered. Okay, yesterday, just as a review, we talked about something called continuity correction. Okay, continuity correction comes from when we have discrete data in the background. This is the boxes represent our binomial distribution data, okay, that have sifted into, you know, a shape like this on their own. We're going to talk about that a little bit more today, why that happens. But we're fitting it with a continuous curve. Okay, so this is our normal, this smooth curve here is our normal curve. Okay, And then what happens is we need to be able to do what they call a continuity correction, because we're talking about whenever I fit like a smooth curve onto a discrete data set, you can see the boxes. Remember when you did this in Calculus 1, the Riemann sums, right? I've got a little bit of overestimating, a little bit of underestimating. So our continuity correction takes that into account. So we went through examples yesterday where we said each box represents a 1 unit, okay, along my x-axis. Okay, so that when my normal curve comes, it basically passes through the exact midpoint of that box. Okay, that's where my value is, that A value. And so we went through all the different examples, the probability that x is equal to A. What do I have to do for that continuity correction? I want to get that whole box in there, so I have to take H that's right in the middle. So I have to adjust either by subtracting a half or adding a half. We're doing a half because that's a 1 unit box. So I have to subtract a half to get this portion of the box, and I have to add 1/2 to my value of A to get this portion of the box. And we went through all the different examples here, okay, for how we were going to be thinking about our continuity correction. So we'll do a couple examples today where we actually want to be able to use a continuity correction for it. General rule of thumb is I can do a continuity correction when I can do a continuity correction when my n times p is greater than or equal to 5 and my n times q is greater than or equal to 5. So we want to make sure that we're basically talking about like a fairly large set of data, you know, that we're working with, so that we're not that we don't have just too few data amounts to be able to do this fit of a normal distribution onto a binomial data set. Okay, so quick background, continuity correction, and then I'm going to start off doing an example with the continuity correction, okay? All right, so I'm on my example sheet. This is example 8, okay, that I'm taking a look at for chapter 4.3, which is our normal probability distribution function. Okay, so example 8 says, a study reports that 6% of American drivers read the newspaper while driving. If there are 300 drivers that are selected at random, let me make sure this is on. If we have 300 drivers that are selected at random, we want to find the probability that exactly 25 say that they read the newspaper while driving. Okay, so we've got all the drivers in the country. This is often what happens in statistics. We have the total population of drivers in the United States, but we're going to take a sample of 300 and we're going to poll them, and we're going to use, ultimately we're going to talk about this as we go, we're going to use this sample of 300 to extrapolate information about the whole population set. We haven't gotten there yet, but this is where we're headed in terms of concepts, okay? So I have 300 drivers, 6% of them in general reveals that, or 6% in general is our study, and then we take 300 out of some larger sample set. We want to find out what's the probability that exactly 25 say that they read the newspaper. Okay, so let's write down, let's kind of start taking notes about some of the stuff that we have here. So in terms of 300 is our sample size, that's our n, that's an n, that's our n value, okay? Our p, our probability, I'm going to take that 6% becomes our probability, right? So 6% is, in terms of probabilities, is 0.06, okay? Which means that my q value is 1 minus p, so the q is equal to 0.94, okay? So now we need to think about, we have the sample size, the n times p and the n times q, in order to be able to do a continuity correction. So let's just do a quick check. So first off, can we do a normal approximation? Okay, can we do this a normal approximation to this curve? Now it's binomial because, right, do you read while driving, yes or no? So you can see how that's going to fit into a binomial type of a question. So can we do a normal approximation? So our mean is going to be n times p because it's binomial. So our n is 300, our p is 0.06, and we multiply those out. This is 18, which is greater than or equal to 5. So it satisfies my n times p is greater than or equal to 5 in order to do that. Let's also check for n times q. N times q, 300 times 0.94, which is equal to 282, which is also greater than or equal to 5. Okay, so it satisfies our requirements for being able to do a continuity correction. So So we can do that. All right, so let's check. So I'm going to write out, we've got our mean value. Our mean value is 18, right? So I need to be able to figure out my standard deviation. My sigma is going to be, excuse me, n times p times q square rooted. Okay, this comes from, we talked about this yesterday, right down here at the bottom. So we said for binomial data, our mean is n times p, and our sigma, our standard deviation, is n times p times q square rooted. Okay. All right, so n times p times q, we're going to plug these things in. So this is 300 times 0.06 times 0.94. Take the square root. So then I get my standard deviation is equal to 4.11. So I'm kind of prefetching some of this information that I'm going to need. All right. I'm going to scroll up a little bit. And now the thing that I need to think about now is I have to take a look at what's the probability that x, my random variable, is equal to 25. Okay, we didn't specify a random variable in this problem, but we're going to assign one. We're going to say x is the number of drivers that read while they're driving. So we're going to say what's the probability that that random variable is actually equal to 25. So we need, in order to do this, we need a range of values. We need a range of values anyway when we're doing these things. And we also need a continuity correction. Right? Because let's think about it. We're doing a binomial. We have binomial data, right? So this is our 25. So this is, if you think about like that graph that we did with all those boxes, right? This kind of a box right here. So 25, okay, is the thing that we're looking for here. And now our binomial, our normal fit kind of comes along and it cruises right along here. So you can see, right? What we want is, you know, I've got this. I want to know exactly, I want to be able to get what's the probability that x is actually equal to 25. So what I need to do is I have to include this whole box that represents 25. So that means that I need to include, you know, this value and this value here. So this value at this end is, it's a 1 unit box. So this value is 25 minus 1/2. This value right here is 25 plus 1/2. Okay. That's our continuity correction, which is we're taking the both sides of that box, okay, and we're going to include the area inside of this box here, and that's how we're going to be adjusting the fact that we're curve fitting a smooth continuous graph on top of a boxy discrete set of data. Okay, so now what we're really, yeah.
Let's say that your n times q or n times p was not greater than or equal to 5. What would your answer then be? Would you just say we can't do this?
Yeah, so then what I would do is I would probably just use the binomial distribution data for it. I wouldn't do a normal approximation fit on top of it because I wouldn't have a large enough sample size. So I would just use the binomial distribution for it. Because it's a binomial, it's a binomial experiment, right? Do you drive, you know, do you read while driving, yes or no? And then that's your binomial data. So then you would just do your whole binomial set. Does that answer your question?
Yeah.
Talk as we go in the next, as soon as we finish a couple of the examples, we're going to talk in experiments. To have any kind of experimental power, you need to have a certain number of like samples in your sample size in order to really run experiments and be able to make statements and judgments about the overall population size. So we're going to talk about that as we go along. And so if you can't sort of satisfy this minimum requirement, right, then, you know, maybe your experiment actually needs more power in it. So you need to probably go out and gather more data, just as a rule of thumb in general. Okay, so let's go back to this. So the continuity correct, I have to subtract 0.5 from 25 and add 0.5 from 25 to get the bounds of that whole rectangle. So that's going to change this to be the probability that x is between 25 minus and 25 plus. Okay. All right, so that means that, let's add it together. So probability that x is between 24.5 and 25.5. So this is what we're looking for right here. Okay, that's with our continuity correction. And that means that I'm fitting a normal distribution on top of a binomial data set. Okay, so let's do it. We need to calculate z values for each of these things. Okay, so let's calculate I need z values for each of these. Okay, so I'm going to need to figure out. So remember, our z was our transform that took our data from our mean x values of 25, x values of 30, x values of 100, whatever, and it transferred them down into a standard normal table so that I can just use this one table to look up all my values, and I don't need 40 million tables for each particular data set that I'm trying to do. So this is x bar minus my mean all over my standard deviation. So the x bar is what we've been calculating here. That's our particular value. So we're going to do the first one, 24.5 minus the mean we said was 18, because we calculated that 18 right here at the beginning. Okay, so some of these problems will give you the mean and the standard deviation, and some of them, like with the binomial continuity correction fit, you can calculate it yourself. So we've calculated the mean of 18. We've also calculated the standard deviation as 4.11. So when I do this for 24.5, I got a z-value of 1.58. Now I'm going to do the z-value of 25.5. And I calculated my z-value as 1.82. So now, right, I'm going to use these z-values to look up in my my z-table. I hope you guys all have had a chance to print out a copy of this. You'll want to make this into a printout. I did mine two-sided as a printout. You'll want this because you're going to be using it to look up values on like the tests and the quizzes and the homeworks and whatnot. So have this on hand because you're basically going to be using it for the rest of the semester. Okay, so I'm looking this up. So now I'm going to use these values here. So I'm looking at the probability that z is less than or equal to 1.58. Remember our, oops, sorry. Remember our z table tells us values z, the probabilities that are less than or equal to that z. So when I look up on my table, I get for 1.5, I get 0.9429. And the probability that z is less than or equal to 1.82 is equal to 0.9656. Right? So that what I want is a range of values between those. So I'm going to subtract out the smaller from the larger. Z is less than 1.82 minus the probability that z is less than 1.58. Okay, when I subtract these out, 0.9656 minus 0.9429. These are probabilities now. And I'm going to get 0.027. That's my probability. In terms of like percentages, right, I can say that there's a 2.7% chance that exactly 25 drivers read, oops, while driving. Okay, so that's how we would read that from probability to percent. Probability is still a valid answer. You don't have to convert it to percent. This is just how we would, like if we were writing a paper, we would say this is our probability. We would say this is what it means. You'd want to summarize it so people would know what that meant. Okay, but I use my z table to look up the values. Given the z values, what are the probabilities in my z table? I'll give you guys a chance to finish writing up, and then we'll move on to the next example. Okay. Can I change the, is anybody still writing? You want me to wait? Okay, good. All right, so example 9. Example 9 says, approximately 10% of Americans are allergic to ragweed. If a random sample of 200 people is selected, find the probability that 10 or more will be allergic to ragweed. So we're reading these questions, we're kind of starting to, deconstruct what's being said so that we can say, okay, 10 or more, that's different than exactly, right? And this is going to give us our n value. This is going to help us give us our probabilities. Okay, so what we're looking for is this. 10%, right, is going to give us our probability. So P, 10% is 0.10, which means that our Q is 1 minus P, which is 0.9. Okay, so now what I can do is I can say my N is equal to 200. I have to do that quick check to see that N times P, so this is 200 times 0.10, which is 20. That's my mean, which is greater than or equal to 5, so we're good. And my n times q, also, n times q is going to be greater than or equal to 5, so we're good for that too. So while we're here, we'll calculate out our NPQ, okay, which is our standard deviation, rooted, which comes up to be 4.24. Okay, so we've got our standard deviation and we have our mean. We're going to use those in our, whole statistics calculation. Okay, so let's think about what's being asked. So they want the probability that 10 or more. Okay, so what I need to think about is like this. Right, so let's think about our sample, right? So our mean is equal to 20, right? So our mean is equal to 20, and then we're asking for 10. The probability that 10 or more, okay, is going to be equal to that. So this shaded region is what we're looking for, right? But remember, our z table only tells us probabilities to the left. So that means I have to think about, to take the whole area under my curve, which is equal to 1, minus, and I have to subtract out the area under the curve that's less than or equal to 10. And that's going to give me what's left over. It's going to give me what's greater than or equal to 10. Okay. So now I have to calculate my z values for 10. I have to calculate what the probabilities are so I can subtract it from 1. And then that's going to give me the probability here. Okay. So we also need to think about our continuity correction. Okay, because we're talking about a data set and we're employing a normal distribution on top of it. So our continuity correction, so I'm going to go like this. So here's my box that represents 10. So it's going to hit right there. Okay, so my normal distribution says 10 or more, which means I want the whole value of this box because I want to get everything else that's in here. Because I need that. It's not just greater than 10. I want to include 10 in that, and I want to get more than that, which means that the value that I'm looking for, I have to include that smaller end of that box. That's going to be 10 minus 0.5. Okay, so what is what I'm looking for? So I'm looking for the probability that x is greater than or equal to 10 is going to be, with our continuity correction, the probability that x is greater than or equal to 9.5. This is our continuity correction right here. Okay. So now this is what we're going to be calculating our z value based off of. Okay, so I'm going to go my z value of 9.5. Okay, so I'm going to plug that in. So I'm going to say 9.5 minus my mean all over my standard deviation, 4.24. Okay, so that gives me a z value of minus 2.47. The minus is totally fine. The minus just means that it's on the lower end, right? It's less than my mean, right? So I'm over here. If my value was greater than my mean, then I would have a positive z value. So the negative just tells me which side of the normal curve I'm sitting on. So minus 2.47, that's the z value. I'm going to look it up on my z table, and it's going to give me a probability. So this says, I'm going to go the probability that z is less than or equal to minus 2.47, because remember, that's our table, okay? So the probability that's less than or equal to that, oops, sorry, I wrote less than or equal to, is equal to 0.0068, okay? Because our table tells us probabilities that are less than or equal to that value. Because I want more than, remember, we're going to subtract this from 1. So what we did was we just found this value here, which is 0.0068. We have to subtract it from 1 to find this value right here. So the probability that x is greater than or equal to 10 is equal to 1 minus 0.0068, which is equal to 0.9932, which is like saying we have a 99.32% chance of finding somebody. If 10% of Americans are allergic to ragweed, we have a 99% chance that out of a sample of 200, we're going to find 10 or more. Okay, so it's a pretty high probability with our continuity correction. I'll give you guys a chance to finish writing that. This stuff here you don't have to write on an exam. I'm putting that down. You don't have to do this on an exam or on a quiz or on a homework. I'm putting these down for you to be able to visualize what it is that we're doing. I find it very helpful to kind of think it through, like how I need to do this, especially as you're learning this material and as you're remembering and learning what our z-table represents, right? It helps to remember like the kind of the math that you need to do, okay? Just sort of visually speaking. I'll continue to do these things so that you can remember and learn what these things are all about. Okay.
Why did we only do one continuity correction for this problem?
Yeah, we only needed to do one because the nature of the problem says 10 or more, right? If it said exactly 10, right, then I'd have to look at, I'd need to find the bounds from here and a bounds from there and get the value just in that box, right? If it says, I want to do, you know, less than 10 or more than 10 or less than or equal to or whatever, then I would only need to do one continuity correction on it. The way that the problem was defined. Does that make sense?
Yes, thank you.
Okay. All right. Is anybody still writing? I'm gonna move on. I'm gonna move this paper away unless somebody tells me that they need it.
I have a question on the top part. So do we need to show that we can use a normal approximation every single time? So we have to do NP and NQ and show that the value is greater than or equal to 5?
You know, technically speaking, you should show it because you want to be able to show that you're employing these approximations correctly and in the right way. So technically speaking, you should. As we go through, you're going to see, right, we need to calculate n times p in order to get our mean value, right? So if you multiply n times p and you get a value that's less than 5, that's your red flag, right? Because then automatically it's going to bum out. You're going to do this calculation because the mean is equal to n times p. You're going to do that calculation every time anyway, because you need that mean value in order to do the rest of your work, like to calculate the z values and stuff. So when you're doing this, right, if you get a value that's greater than or equal to 5, just go ahead and keep going, right? You don't, I think maybe, I don't know, if the problem says, can you do this and should you or whatever, then obviously you'll need to do the n times p and the n times q in order to show it for reals, but you're gonna have to do this anyway. So that's kind of, it should be there in the back of your mind. Are you getting a value that's greater than or equal to 5? If you do, then go ahead and proceed. If not, then stop and just go back to the binomial distribution.
Okay, thank you.
So these can all be calculated using the regular binomial distribution?
No, so this is what we're heading into the next topic. So what happens is in the next topic we're going to talk about essentially the law of large numbers. As you pull more and more and more people, and typically it's like more than 30, like 30 or more people is like considered a largish number. But as you get larger and larger sample numbers, your data naturally form into a normal distribution curve. So even though your underlying experiment is binomial, right, which is, does this happen, yes or no? Okay, your underlying experiment is that, but your data themselves pull into the normal distribution. So you don't want to use the binomial, you want to use the normal distribution, because assuming that things are normal is going to give you a whole massive amount of statistical power to be able to do a lot of different things. If you have, if your data set is small, right, and then and you can't do, you know, normal approximation because your data set is too small, there's two things. One, you can do it anyway and just say, well, our data set is small, this is preliminary results, we think it's going to extrapolate into larger numbers, and so then that will give you you know, data to be able to go gather more data to say, okay, I think we're on the right track. That's kind of typically how it happens in research, right? Is that, you know, you start off, you try, you know, smaller sample set, you see where the data is taking you. You generally assume that things are normal unless otherwise, unless you're seeing something otherwise. And then you keep trying to gather as much data as possible. We just talked about, like, because the background data is binomial, if you have a really small sample set, like your n times p is less than 5, then you just might as well use the binomial because you don't have the statistical power to be able to do a normal approximation. But that's just kind of a clue for you that you should go out and really gather more data. This is probably a longer answer than you needed, but.
Oh, okay. Thank you.
Yeah, sure. All right. So with that said, let's go into our, this is still in the same chapter, but our next concept is called the central limit theorem. and it's like a long word, and I'm going to give you the definitions and we're going to talk about it. But basically, the underlying essence of it is that as we gather more and more and more data, okay, and the data is, the underlying experiment is a binomial experiment, the data naturally sift themselves into a normal distribution curve, okay, which means that we can use the normal distribution to do a lot of statistics on it, because that's naturally where a lot of data head. Unless it's something like gamma radiation or meteor showers or whatnot, where they naturally fit into a Poisson curve, but data in general from an underlying binomial go into a normal distribution. But let me write down the definitions, but just in the back of your mind, that's what we're talking about. So the central limit theorem. So we're going to say, how do the means of the samples of the same size taken from the same population vary about the population means? Okay, I'm going to talk about sampling stuff, and then we have like sampling errors and things that we need to take into account because we're gathering, you know, large sample sizes. But let me keep going with the definitions here, and then we'll go into the math of it. Okay, so the sampling distribution okay, let me write these down and then we'll talk about it. Of sample means is a distribution obtained by using the means computed from random samples of specific size taken from the population. Okay, so now what happens is we're starting to move into the realm of, I have a large population, like all of American adults, and I want to just take a sample of adults from across the country or sample of adults from one region or another, and I want to be able to ask them questions or do surveys or whatever, and I want to be able to extrapolate back to the whole population. So I've got like different types of errors and different types of things that I need to think about, right? As I go from a large population to a sample size, how do I adjust for that? Okay, so we're talking about, we have a sample distribution. Okay, so I've got, within that sample, I've got means, okay, within this distribution, okay? These are a lot of words. We can write them down. I'm trying to give you the formal semi-formal definitions of what these things mean. Scroll that up just a little bit. Okay, so then when we sample, we have a sampling error. Okay, so the sampling error is the difference between the sample measure and the corresponding population measure. It's always of trouble in statistics. Like I said, we go from all of America to a sample of 1,000 people, and can we really extrapolate out from that sample of 1,000 people or a sample of 200 people to make statements about all of America? This is kind of like what happens in statistics. Okay, so we have a sampling error. So sampling measure. So what this means is the sample is not a perfect representation of the population. Okay, these are all parts of, we're going to spend a lot of time talking about different types of errors and how we do that. Make sure you guys have those definitions, and then we'll start moving into the math. Go up just a little bit. Okay. So let me write down some assumptions. So the mean of the sample means will be the same as the population mean. Okay, so we're saying that our expected value of our sample is equal to our population mean, which we're just going to call our mean. Okay, so we're making some assumptions, right? I'm going to take the sample, I'm going to figure out what its mean is. I'm going to make the assumption that it's going to be the same mean within some, we're going to talk later, within some confidence, within some, sampling error. Okay. Standard deviation of the sample means will be smaller than the standard deviation of the population. I have a smaller sample size that I'm working with, right? So probably there's less variance when I'm working with a smaller population size. So my standard deviation of the sample is going to be smaller than that. So I need to be able to adjust in my calculations. Okay, when I go to calculate my normal distribution and my z-values and everything, I need to be able to adjust the fact that I'm talking about a sample and not a population. So then we talk about our standard deviation as being adjusted by the square root of our sample size, n. So population standard deviation divided by our sample size. And this comes from, it's the variance divided by the sample size. So this is sigma squared divided by n, which is our variance over our sample size. Okay, so that's where we get this, oops, sorry. That's where we get our square roots from, right? Because we are, right, our normal curve deals with standard deviations, okay, but the variance is actually like our mathematical term that we're thinking of. So our variance divided by our sample size, but because we're dealing with our standard deviation, we take the square root of the top and the bottom to get the standard deviation. But that means that I'm dealing with the square root of my sample size here, okay?
It's also the population variance.
Yeah, variance population. Yep. And we'll tell you that in the problem. So say the population standard deviation is this, and so you'll know. Okay. If you guys have all this stuff, I need to flip the page. Anybody still writing? Okay. All right. So let's talk about this in terms of our z-value. Okay, so that means that now when we go to calculate our z-value, okay, remember it was x bar minus mu, we did it divided by our standard deviation, which was a good intro to think about things. And we knew our mean, we knew the standard deviation, but now we're dealing with populations versus sample size. So in the denominator itself, okay, be careful about doing this on your calculator with the order of operations. I see often people make, they get this mistake because they go x bar minus mu divided by sigma divided by radical n. But if you're going to do it all in one fell swoop, make sure you put parentheses around the terms in the denominator so your calculator gets the order of operations right. So this is the way that we're going to be calculating our z values to adjust for sample versus population. So when n is greater than or equal to 30, typically as a rule of thumb, you have a large enough sample size that the distribution is normal unless otherwise stated. Okay, this is our law of large numbers. 30 doesn't seem like a very large number, but it's large enough to start to get confidence that our binomial data actually is fitting into very nicely into a normal curve. So we can, often you'll see in, in the problems that we're working on, we'll say you can assume the data are normally distributed. And so that allows us to use our normal probability density function as a way of estimating the probabilities of all of the data behind the scenes. And that gives us a lot of statistical power because the normal curve is pretty powerful. Okay. All right. So with that, I'm pulling out my example sheet and looking at example number 10. Okay. So the survey shows we've got children ages 2 to 5 years old watch an average of 25 hours of TV per week. And we're going to assume that the data is normally distributed and it has a standard deviation of 3 hours. Now we're looking at if we have 20 children between in this age group, 2 to 5 years, 25 children are selected, 20 children are selected. What's the probability that they watch more than 26.3 hours of TV per week? Okay, so let's take a look. So I've got my population. My population mean, they said, was 25 hours of TV per week, right? So my mean is 25. My population standard deviation is equal to 3 hours. So I'm kind of pulling things out of the question, okay, to kind of put them into their spots. I'm kind of taking notes as I'm reading this question. Okay, so then our sample size is equal to 20. Okay, so that's our n value. N. All right, so now what we want to know is what's the probability that our random variable x is greater than or equal to 26.3. Okay, x bar. All right, so I need to do a z transform on this in order to use my z table to look things up. So the first thing I'm going to do is I'm going to calculate my z. So my x bar, I want that minus mu all over sigma square root of n, because we're doing the population to sample size now. So this is 26.3 minus 25 all over, I'm plugging things in, 3 divided by radical 20. And I'll put this in parentheses just to help keep us honest about it.
Didn't you say our n had to be greater than or equal to 30 though?
Yeah, it's funny, you know, so when the n is greater than or equal to 30, we can assume that the data is normally distributed unless otherwise stated. We can still make this assumption. See, I told you, assume the data is normally distributed in the problem. So I'm telling you that it's normally distributed, which allows us to use the normal curve and the normal statistics in order to do this stuff. So even though our n is less than 20, right, because we're assuming that the data is normally distributed, we're going to use our normal distribution curve and our normal distribution probability tables. Totally fine. You can totally do that. As we go along, when we get into different types of this is an intro into like the normal distribution. We get into later chapters, we're going to be talking about different types of normal distributions that take into account the fact that we have a sample size that's smaller than 30, and then and so then those table values reflect that we have a smaller sample size. We haven't gotten there yet. That's in later chapters. We'll get there. So for now, I'm just telling you, we're going to assume it's normally distributed. It's okay that our n is less than 30 because we're making the assumption it's normal. I can't just assume that it is because my n is smaller than 30. All right, so now when I calculate this out, 26.3 minus 25 divided by 3 over radical 20, I'm going to get a z value of 1.938. So this is the z value that I use to look up in my table. I go to 1.9 and I look up for 3, and I'm going to make an approximation for this 3.8 value. Here, maybe I'll go up to 1.94. So this is the probability that z is greater than 1.938. So they said they watch more than 26.3, so I'm looking at 1.938. So remember, to get a greater than value, I'm just going to draw this out here. Right, here's my z equals 1.938. Right, I want this probability right here, that area under the curve, but my z table tells me everything that's less than that. So I have to take my whole curve, which has a probability equal to 1, and I have to subtract out my z equals 1.938, the value, the probability value that I find for here. So my z table gives me this value. I subtract it from 1 to get the values that are greater than that. So this is going to be 1 minus, I look up this z value on my table and I find it's 0.9738, that's a 9. 9738. You guys can cross-check that on your tables too if you want. So that means when I subtract these out, I get 0.0262 as a probability that children, this random sample of children, is going to watch more than 26.3 hours per week. So we're saying that there's roughly a 2.62% chance is how we're going to read that. That this, if we select 20 children, then what's the probability that they watch more than 26.3 hours per week is 2.6. Kind of a low probability. Okay. You guys a chance to finish writing that. Okay. Does anybody need more time to keep writing?
For when you calculate the z, are you just taking the value at 1.93?
You could even go 1.94 because this I can round up. Because when I look at my graph, right, I'm looking here. I go 1.9, and then I go over to 0.4. It looks like, yeah, it looks like I did 1.94. So you know, because our table only goes up to here in terms of significant values. The rest of it you'll have to extrapolate, and you can use your judgment on that one.
Okay.
Be flexible. I mean, if you chose 1.93 and I chose 1.94, our values aren't going to be too far off. They're going to be maybe off like right here, you know, in this area, right? So then our values here will only be off a little bit. So I mean, I'll be flexible when I take a look at it. Just make sure when you guys are taking the test or the quizzes or homeworks or whatever, that you're super clear about how you calculated your Z value. And then you can even say you used this value on your lookup table, okay, to find it, and then that's where you got this from. So that like if you chose 1.93 and I chose 1.94, our answers are going to be slightly different, but they're going to be super close, right?
Okay.
So that's, I mean, I'll be flexible about it, obviously. Like I'm not going to take off points because you chose 1.93 and I chose 1.94. If you calculated this wrong, your values are going to be very different, right? So that's why I need to see your whole logic of how you calculate the Z value and what you're getting, okay? So I can understand your logic on things. Makes it hard to grade, but it's more fair that way. All right, I'm flipping the page. So example 11. So the average, the average age of a car in the US is 8 years, which is in terms of months, 96 months. And the standard deviation is 16 months, okay? If we take a random sample of 36 cars, we want to find the probability that the mean of their age is between 90 and 100 months. So we're doing now a range of values, okay? So this means we're going to be thinking about, I need to find the area of my curve that's between two different points, okay, is how I'm going to be thinking about it. So I've got n is equal to 36, so my n is greater than or equal to 30. So we can assume the data is normally distributed by our central limit theorem. Right, I can do it. See, it didn't tell me anywhere within here, right, that my data was normally distributed, right? It didn't say, assume it's normal. But because my sample size is more than 30, I'm going to make that assumption because of the central limit theorem. I can do that, right? I have more than 36 cars. So that means that I can use my Z table. I can use all the standard normal procedures to calculate things. All right, so let's think about what we're trying to do here. I'm going to just do a quick plot. So I've got my normal data. Right, we've got this average age is 96, right? So that's our mean value. We want to find between 90 and 100 is what we're looking for. So I want to find the area around my mean, but between 90 and 100, okay? Which means that I need to think about things because remember our table only does things that are less than. So first off, I'm going to choose my larger number. So the probability, the area under the curve that's less than 100 minus the area under the curve that's less than 90, right? So if I subtract out that 90 bit, I'm going to get the area between 90 and 100. So these are the Z values that we need to calculate, and then I'm going to subtract one from the other. So I'm going to go, my Z of 90, okay, is going to be 90 minus 96, this is our mean, all over 16, which is our standard deviation, divided by square root of 36. Put that in parentheses here. Okay. Our radical n, standard deviation, our x bar minus our population mean. And this gives me a z-value of minus 2.25. Okay. Let's do it again for 100. I'm going to go 100 minus 96. 16 divided by radical 36. I'll put those in parentheses to keep us honest. And that's going to give us the z-value of 1.5. Okay. These are the values that I need to look up. So the probability that z is less than or equal to minus 2.25 is what my table is going to show me, which is equal to 0.0122. That's a 0. Okay. I looked that up on my table. The probability that z is less than or equal to 1.5, I looked that up on my table, I got 0.9332. Okay, so I'm going to subtract, right, my 90 from my 100. That means, let's see, 100 minus, right? So I'm going to plug these in, so I'm going to get 0.9332 minus 0.0122, and that's going to give me 0.921, which means I've got a 92.1% chance, right, that the mean of the car that I'm choosing, right, the mean of the 36 cars that we're choosing is going to be between 90 and 100 months, given that the average mean of the cars is 96 months. Now let me just write down our little data set here. I didn't write this down before. So the mean was 96. Standard deviation was 16, and our n is equal to 36. So these are the values that we were given in the problem itself. Okay. Right. Anybody need more time to write this down? So that's it for our examples for chapter 4.3. I'll scan these in and then post them later today. I just want to throw out our book talked about a correction factor. We typically don't use this, but because it's in our book, I want to make sure that you guys have it. So what this means is that we're drawing, samples from a population without replacement. From a finite population. You may see this at some point. I'm going to post a sample formula sheet that we typically give out when we teach this class when it's not online, and then so you guys can have it. You can add to it. I'll start posting that shortly. It's kind of like you may not need it at this point because we don't have a whole lot of formulas to think about. But as we progress along in the statistics area, we're going to be accumulating lots of formulas, and so you may see this correction factor on there. And I want to make sure that you guys have it. So let me just talk about, so N, big N is our population size, right? And then little n is our sample size, right? So to calculate our standard deviation, right, for our random variable, we're talking about our standard deviation divided by our sample size, right? So this is our population standard deviation. I've got n minus n all over n minus 1 here. And this gives us, we're going to use sigma sub x in our z calculation. Right, so I'm going to say z equals x bar minus mu, minus mu all over z sub x. Okay, you know, I wouldn't worry about it. Like I say, I'm just putting this out here, you know, just so you guys have it. Sometimes I don't even give it out, but then it comes up, like people see it on the formula sheet, or there may be like something in the book or in like a homework problem, and then people are kind of wondering like what it is. So that's why I'm putting it out there, just so that you have it. But typically we tend not to use it. Okay. Right. So that's the end of 4.3. That's our general introduction to the normal distribution. Okay. Make sure that you guys print out a copy of Table A so that you have that on hand when you're doing problems. 4.3 is definitely on our test. 5.2, I'm going to start right now. Okay. And then 5.2, we're going to be using a lot of things. It's it's an interesting, it's sort of like kind of going back to now that we have all these different probability distributions, how do we think about estimating parameters? So it's a little bit more heavy math focused in terms of as opposed to less theory. But does everybody have this here? I'm gonna swap out this for a new page. Okay, good. All right. Let's talk about chapter 5.2. Okay, so this is a chapter on estimation. Okay, and then basically what we're focusing on is the method of maximum likelihood. Estimation. Okay, there's also the method of moments, which we're not covering. I think that's covered in a class that's the sequel to this one. Okay, they focus more on the method of moments. We're going to talk about the maximum likelihood estimator. Okay, so let's think about why we would do this. So the problem that we have is we've got some random sample. Right, it's good. We've got x1, x2, x3, all the way up to like x sub n in terms of like our samples. Okay, we have random variables. They have values, you know, accordingly here. We don't know what the probability distribution is. Oops, we don't know the probability distribution, but we do know the distribution is going to rely on certain estimators. It's going to rely on certain variables. Okay, so we don't know, like in the previous chapters, we gave you the probability density functions, and we said, okay, what's the mean? What's the expected value going to be? We had different methods for being able to calculate out that that mean value, or even like the variance of that value. But now we've got this random sample, and we don't know what the distribution is, but we want to be able to come up with what we think is a pretty good estimate of what that mean is going to be, right? And so we're given some random sample, and we need to be able to figure out what's an estimate of that mean, or what's an estimate of the variance, or what's an estimate of some other parameter. So we know, right, we don't know what the exact distribution is. Maybe we know that it's normal, or we know it's Poisson, but we don't know all the parameters on there. So we know that the distribution is going to rely on some unknown parameter. We're going to call that unknown parameter theta, just for a variable name, okay? So theta becomes the thing that we're trying to estimate, okay? So that's our problem. Now the goal here is to create a good point estimate of whatever that unknown parameter is. Is the theta, is it our mean value? Is it our standard deviation? That's the thing that we're going to be deciding, right? So we want to come up with a good point estimate of theta, okay, based on the observed values of the random sample. You're learning methods. This is a method where you're working for a biology company, you're gathering all sorts of data, and you're not quite sure what's the like this data that you're gathering, you want to be able to extrapolate for all different, you know, populations of this given type. So you need to come up with an estimate for the mean. And so we're learning methods for how we can make an estimate of what the mean value is for the population based on the sample that we have. Okay, so we've got we got all these observed values, which comes up here from our random sample, and we want to use those observations to come up with a point estimate for whatever our parameter is. Our parameter is going to represent the mean or the standard deviation or something that we need to find. Okay, so we can make assumptions though. So if we assume the data are normally distributed, oops, sorry, normally distributed, then theta is a good estimate of our mean. Typically that's ends up what happening. And to make the assumption that the data is normally distributed is usually fair because most data is normally distributed. Okay, unless it falls under a specific case of like a Poisson, which you would be able to see because the normal distribution, the results that you would get from that would be pretty bad. You'd say, well, let's try a different distribution function. Okay, so we're going to talk about methods. Okay, the method of maximum likelihood is the method we're going to be focusing on in this chapter. And the method of maximum likelihood, it's a long word, but all it says is it's a method for trying to figure out, what's the best value of theta that's going to be the best estimate for the mean or for the variance. Okay, so let me write down the definition for that, and then we'll go into examples. So the method of maximum likelihood.
Could you move the screen up a little bit?
Like that?
Yep.
So we want to do, let me write this down and then we'll talk about it. So we're going to choose as an estimate for theta the value of theta that maximizes the probability, which is our likelihood, of getting the data we have observed. Oops, sorry, you can't see what I'm doing. So what does it mean to maximize the probability? Well, we're going back to calculus 1, right? I have a function. I want to find the function's maximum, right? So how do we do that? If I have some function, I want to find its maximum. I take the derivative. I set it equal to 0. I solve for x, and that tells me the x coordinate, and then I can plug that back in and find out what the y value is. That's going to give me the coordinate, x and y coordinate of the maximum point on this curve, or maximum points, right, depending on the function that we have. So when we do this here, what we're going to be thinking about is our method of maximum likelihood is coming up with an estimator, theta, right? If my theta is estimating the mean on a normal distribution, I'm going to take the derivative of my function, which is going to be my normal distribution, and then I'm going to set it equal to 0, and I'm going to solve for theta, and that's going to give me a value that's going to be an estimate of the maximum likelihood, okay, the maximum probability, okay. So let me write down some things here. Okay. So we've got our probability density function, right, which we typically think of these as being f of y, but it's just a variable. And it looks like it's multivariable, right? It's my random variable is y. Y can take on any value, little y, and theta is our estimator. So it looks multivariable, but theta, it's really just single variable because theta is the thing that we're trying to work with. We also can do this with discrete, so we have a probability mass function. Which we'll denote with f of x of theta. So it looks multivariable, but really, right, theta is the thing that we're trying to maximize, okay? And we're going to do this. We have a probability density function or mass function for each little value of x and y. Okay, so for every value that my random variable can take on, I have a probability density function that has an estimator theta in it, okay? This is like, maybe it sounds confusing. We're going to work through examples so you can see what we're talking about. So we're going to put all these together. Put all of these together into what's going to look like a joint. I'm going to put it in parentheses. It's going to look like a joint probability function. Joint between y and theta or x and theta. And I put joint in parentheses because it's not really a joint distribution, okay? It looked multivariable, but it's not. Theta is the thing that we're working for, okay? These particular values of x and y are our observed values. Okay, so theta is the thing I'm trying to use for that. Okay. You guys, anybody need more time to write this stuff?
Yeah, one sec. All right.
Okay, great. All right. So when we put all of these probability density functions together, right, it looks like a joint function, but it's not, because theta is the thing that we're working for. Once we put them all together, they're in what we call a likelihood function. And a likelihood function, this is, I'm going to put it in parentheses again, the joint, because it's not really joint, but the joint probability function of all the PDFs or PMFs, depending of each random sample x sub I. We'll do some examples so you can see what we're talking about here. And it's going to go into a likelihood function. The likelihood function, we'll call it L for likelihood, is a function of theta. Okay. It looks like it's a function of y and theta, but it's really just theta, because theta is the thing we want to maximize. So this means this is the probability that x1 equals x sub 1, x2 equals x sub 2, x3 equals x sub 3, and so on and so forth up to n. Right, so our big random variable, our little, right, this is, our big random variable could take on this value, right? We've got all these different random variables. This, right, each one is an independent trial, so I can multiply out my individual functions. So this is x1 theta times x2 theta times f of x3 theta times all the way up to f of n, x of n. Okay, so theta is the estimator, theta is the parameter that we want to estimate, and I have all these little values of what my random variable, what I've observed my random variable as being equal to. So I multiply my probability density function with this x1 and this theta. Theta is still like a variable, right? So theta remains as theta, okay? Which means I'm going to write this out as, this looks like pi, but this is our symbol for product. This is big, and this is like, we know how we did sigma was our sum, right? So sum from 1 to n. This is our product from 1 to n. I'm going to multiply all of these things out. This is f x sub I of theta. That's not a j, that's just a semicolon. Okay. So I'm multiplying. This is our product symbol. Okay. That's our likelihood function. It's the product of all of these individual probability density functions. Okay, let's write down what it looks like for discrete and continuous. Discrete, we have random variables x sub I, okay, which means my likelihood function is going to be the product I equals 1 to n ex k sub I and theta. Okay, so this is our probability mass function. I'm multiplying each of these all together because this is where x takes on the value of k sub I. And I'm going to product, multiply them all out from 1 to n, however many I have. Our continuous, the same. We use a different random variable so we don't get confused. So we've got the random variable. These are just names. I could have used any variable name that I wanted. Y sub I, okay. My likelihood function, this is the likelihood function. Okay, so my likelihood function is the product. My likelihood function for continuous is going to be also a product. Looks like a big pi, I equals 1 to n. I've got my probability, what I think is my probability density function. And this is going to be y sub I sub theta. This, we already know, this was our observed value. This little y sub I. Theta is our parameter that we're looking for. We're going to plug this in. We're going to multiply everything out. We're going to take the derivative and solve for theta. Theta is going to give us a value that's going to be our estimate that we think maximizes the probability, right? I think that this, if I'm solving for, if I'm trying to estimate what my mean value is, right? Because I don't know what's the population mean. I just have all these observed values. I need to be able to take all of these observed values, plug them into my density function, multiply them out, take the derivative, solve for theta, that's the thing I'm looking for, and say, I think this is a pretty good estimate for where our population mean is going to be based on these observed values. Okay. But let me just write it down for posterity. So it looks like a joint PDF or PMF, right? Because I've got this y sub I and then theta. I've got two parameters, right? But oops, these things are a function of theta, not a function of k or y. Okay, we already know k and y are our observed values. We already know what they are. So it's not truly multivariable. Oops, I'm running out of space. Okay, I don't want to write that down for posterity. It looks multivariable because I've got these multiple variables in there, but really theta is the thing that we're looking for. Okay. So because we need to find the value of theta that maximizes our likelihood function, which is our probability. We want to find that, remember our probability distribution, if we assume it's a normal curve, right? My mean, right, is going to be at that peak. My mean is my maximum. So that value, that mean, could be our theta. That's the estimator that we're looking for. So I've got this, I'm assuming it's a normal curve, right? I have to take the derivative, set it equal to 0, find out what theta value is going to give me that maximum value. So I'm looking for the value of theta that's going to maximize our likelihood function. And then this value, we call it theta sub e. Sometimes it's also called theta hat, right? So it also can look like theta hat. Some books, they'll call it theta sub e or theta hat. Is our what we call a maximum likelihood estimator. And you'll be asked, what's the maximum likelihood estimator for this function here, given this stuff, right? And so you'll have to go through all that we do. So just the process, we're going to take the derivative of our likelihood function with respect to theta and set it equal to 0, and then solve for theta. Okay, so this is the process on how we're going to do it. How we come up with this maximum likelihood function is what we're going to be learning right now. Okay, but we're going back to our calculus 1, taking the derivative and doing this. Okay. So this is a method for trying to come up with the mean of this population given this sample set that I have here. Okay, or what's the variance of this population given this sample set? Does anybody need more time to keep writing? Okay. So I've got my lecture example page for chapter 5.2. Okay, so make sure that you pull yours out. We're gonna start going through some examples. Right. So 5.2. So right, we've got 4 random variables. Okay. Each of these random variables follows a Poisson distribution. So remember our Poisson distribution from a couple days ago. So we're telling you what the underlying probability density function is. So our random variables x1 equals 3, x2 equals 5, x3 equals 4, x4 equals 2. We want to find out what's the maximum likelihood estimate for lambda within our Poisson distribution. So I'm going to start taking notes. So our Poisson looks something like this. I've got e to the minus lambda times lambda raised to the nth power all over n factorial. Okay, is my Poisson distribution, right? So now I need to find a maximum likelihood estimator for my lambda. Okay, so I'm going to start writing lambda, my likelihood function of lambda, right? To remind me of what I'm trying to do. So for each of these values, right? Each of these values here is going to give me a particular value here. So I'm going to go, let's start plugging in. So e to the minus lambda, lambda to the 3 all over 3 factorial times e to the minus lambda, lambda to the 5. See, I'm taking each of these random values, right? That was 3, that goes in here, all over 5 factorial times e to the minus lambda, lambda to the 4, all over 4 factorial times. I'm going to take the last one, e to the minus lambda, lambda to the 2, all over 2 factorial. Okay, so this is my likelihood function I was told it was Poisson. This is my Poisson distribution. Lambda is the thing I'm looking for. N are the observations that we have, right? And they were not even told like what these values are. Is it like the time between things? We don't even care. We're using this as an example. Okay, so these are different observations. So I'm plugging them in. Remember, our likelihood function is the product of all of these different probability density functions using each of the observational values that we found. Okay, so I'm going to put all of these together using my law of exponents to come up with one function. So this is going to be like the product, right? I equals 1 to 4. I've got 4, 1, 2, 3, 4 different random variables. So I'm going to multiply all of these together, e to the minus lambda, lambda to the n sub I, over n sub I factorial. Right, so that's what I just did right here. Okay, so now when I do this, I've got e to the minus lambda happening 4 times. So it looks like e to the minus 4 lambda. Okay, I'm using my properties of exponents. I've got lambda as a base, and I've got the exponents of 3, 5, 4, and 2. So I'm going to add these up. 3 plus 5 plus 4 plus 2 gives me 14. And now here at the bottom, these are all just being multiplied together. Okay, so this is the nature of what we're trying to do. We're multiplying together all of our probability density functions. This was actually doing it out. Okay, and then this is what we get when we combine all of our terms, all of our like terms, right? I added up the exponentials, I added up the exponents of the exponentials that had the common base, which is how I got minus 4 lambda and 14 here. Okay, so now my goal is I need to maximize my L sub lambda and be able to find out what my lambda value is. So I have to take the derivative. But that's going to be a pain because there's a lot of stuff I've got. Well, you know, the factorials in the denominator are just a constant, but I've got the product rule. So I'm going to use logarithmic differentiation to help me as a trick for figuring that out. So I'm going to use logarithmic differentiation. You don't have to, but you're going to find that it's going to make your math a lot easier if you do that, especially as we get into the normal distribution. All right, so that means I'm going to take the natural log of my likelihood. You have to do the natural log of both sides. So I have to take the natural log of this and the natural log of e to the minus 4 lambda, lambda 14 all over 3 factorial, 5 factorial, 4 factorial, 2 factorial. I'm just going to leave it like that. So remember our properties of logs, right? Things that are being multiplied together are added. Things that are being divided are subtracted. Things that are in the exponent can come down out front. Natural log of e is equal to 1. So let's just write this out. So ln of e to the minus 4 lambda. I'll write this all out at first just so you can remember. Plus the natural log of lambda to the 14 minus the natural log of all these factorials there. So let's work on our exponents. So this is going to be minus 4 lambda natural log of e, which is going to be equal to 1, plus 14 natural log of lambda minus the natural log of, I'm just going to write factorial. That's my shorthand, so I don't have to write out all those terms there. Okay, that's what that means. 3 factorial, 5 factorial, 4 factorial, 2 factorial. So this is, I've got the natural log of the likelihood function equals minus 4 lambda plus 14 natural log of lambda minus the natural log of all these. This is just a number, right? I'm just going to leave it like that for now. Oops, there we go. Right. So I need to maximize this function right here. So I need to take the derivative of this function with respect to lambda. So I'm going to take the derivative with respect to lambda. I have to take the derivative of both sides. So that's going to give me, the derivative with respect to lambda gives me, right, minus 4 plus, I've got 14 as a coefficient, but the natural log, right, gives me a derivative 1 over that term here. And then this becomes 0 because it's just a constant term, right? I need to set that equal to 0 and solve for lambda. Solve for lambda to find out what the value is going to maximize it. So I get minus 4 plus 14 over lambda equals 0, right? I get 14 over, oops, that's a lambda equals 4. Then I'm going to get lambda equals 14 over 4, which is like 3.5 is our maximum likelihood estimator for lambda, okay, for our exponential. So let me just write that out in words. So 3.5 is maximum likelihood estimator for lambda. Well, so what does this mean, right? So we went through the math and did it. So we think we've got all this, we've got some process that's happening we think is represented by a Poisson distribution, we're pretty sure. And I gather random variables for it, right? I've got my first random variable is equal to 3, my second random variable is equal to 5, my third random variable is equal to 4, my fourth random variable is equal to 2. These are observations, right, from data that I'm gathering. I'm pretty sure it's Poisson, you know, I'm fairly confident it's Poisson. And so, but I need to be able to figure out what's lambda in my Poisson distribution because I don't know. All I have are these 4 observational values. So I'm going to plug each of these 4 values into my Poisson distribution. I'm going to multiply them out because each one is an independent file. And I'm going to use that product to help me calculate, help me calculate what that lambda value is by taking the derivative, setting it equal to 0, solving for lambda. That gives me, based on the observations that I have, a reasonable estimate of what lambda could be. It's the estimate of lambda that's going to maximize the probability of my Poisson distribution. Okay, that's why we're doing this, because we don't know what lambda is. We just have all of our observational values. Okay, I'll let you guys finish writing that, and then we'll try some more examples. Maybe we'll work through one more example, and then we'll continue on tomorrow. We'll do some more of this stuff tomorrow. Okay. Does anybody need more time writing this before I turn the page? And everybody's good? Okay. I'm going to turn the page. So I'm looking at example 2. Right. So we've got this random sample, x1, x2, xn, where this could be a 0 or a 1. So if we poll all these people, does the person have a sports car, yes or no? If they don't own a sports car, x sub I is equal to 0. If they do own a sports car, x sub I is equal to 1. So it's just a 1 or a 0, okay? So each of these polls, each of these, you know, I'm going to talk about all these different people. They're independent, what we call, I'm trying to use these terms, Bernoulli random variables. All that means is it's a binomial experiment. It's a success or failure. Success means we do own a sports car. Failure means we don't own a sports car, right? Success is assigned to 1. Failure is assigned to 0. Okay, so that's, I'm trying to use these terms here so that when you read it in your book or elsewhere, you'll know what that means. We don't know what P is, right? So, which is our probability of owning a sports car. We want to be able to come up with a maximum likelihood estimate of P, which is the proportion of people who own a sports car, which we can talk about as being our probability. So let's start kind of taking notes and write down what we have. So then if x sub I are independent Bernoulli random variables, okay, then the probability mass function for each x sub I is going to be simply, I'm going to say my function x sub I, gamma p, is going to look like this. I'm going to say I've got p raised to the x sub I, or 1 minus p raised to the 1 minus x sub I. Think about it this way, right? X sub I is equal to 1 if the person owns a sports car, right? If it's equal to 1, then my probability mass function is equal to p. If the person does not own a sports car, right, x sub I is equal to 0, so this term becomes 1. This term becomes 1 here, and I get 1 minus p, which is that the person doesn't own a sports car. Okay, so in any particular x sub I, I'm either using this one or I'm using this one. You can do it out for yourself and try it out. So when this is equal to 1, this term is valid. This term becomes a 1. When this is equal to 0, right, when this is equal to 1, then this becomes a 0. So that makes this term 1. when this is equal to 0, this term becomes 1, and then this term is the one that's active. Okay, so only one of these two is actually happening at any given time, right? Because of the nature of our x sub I value. Okay, let's just write that down. So x sub I is either a 0 or a 1. Okay, and our probability is between 0 and 1. Or always remember, your probabilities are between 0 and 1. Okay, and I could make this inclusive here. Right. So let's talk about our likelihood function. And we're really trying to explain all the background on this stuff. So the likelihood function, so the likelihood, we're trying to find the likelihood estimator of P is what we're trying to go for. So it's the likelihood function of P, and it's going to be the product, right, from I equals 1 to n. How many of these samples are we actually getting? And we're going to go out there and we're going to take a look at what's our function itself. So I'm going to plug this in. So this is going to be P x of 1, 1 minus P, 1 minus x of 1, oops, 1, times P x of 2, 1 minus P, 1 minus x of 2, and times we're just going to keep going all the way up to P to n, minus P, 1 minus x of n, right? So n being the total number of people that we've polled, right? So this is, it's just a product of all of these just different terms. Okay, so now I've got my product. So always with these products, I have to think about summing my exponents, right? Because I've got P to the x of 1, P to the x of 2, P to the x of 3, all the way. So I've got the base is the same here, just like it is here. And I have to think about how I'm going to sum all the exponents. So I'm going to sum my exponents now, right? So I'm going to think about L sub P is equal to P, right? I have to sum up all of my x sub i's, right? I can't just, because the x sub i's may be different. Remember when we have exponents, right? We're going to be summing up those values if they're the same base. Same thing here, and minus x sub I, okay? So this is how I'm summing these up, right? Everybody see how we're getting these as exponents here. So now, right, this is our maximum likelihood function, right? I've gone from a product to values that just have our summations and the exponents here. So to maximize this, I have to take the derivative. Right, so I have to find the P that maximizes L sub P, which means I have to take the derivative. But first I'm gonna think about doing logarithmic differentiation because it's gonna help me separate out all of these things, especially if I've got my terms in the exponent here. So I'm gonna take the derivative of both sides. Natural log of P sum x sub I, 1 minus P, and minus the sum of x sub I. Okay, so I'm going to take the natural log of both sides. Now remember our properties of logs, I can split these up. So this is the natural log of P to the sum x sub I plus natural log of 1 minus P and minus the sum of x sub I. Okay. Remember I'm going to put parentheses around this because that stays in a block. Now remember what happens with exponents. This becomes the sum of x sub I, natural log of P, plus this whole thing. Remember, I'm going to put this in parentheses. Natural log of 1 minus P. Be careful. People do all this stuff really nice and beautifully, and then they forget to put parentheses around the n minus the sum of x sub I. And they go n minus the sum of x sub I, and then they forget that this n is actually attached to the natural log of 1 minus P, and they think it's just kind of floating on its own. So put parentheses around your exponent terms so that you don't lose track of them. All right, so now that we've got this, let's go ahead and start thinking about, go ahead and start thinking about taking the derivative. With respect to P. So I'm going to take the derivative, ddP, of our, we have to do both sides, right? So I'm going to take the derivative over here with respect to P. So I've got the sum of x sub I is a number, ln of P, right? So I've got sum of x sub I is my coefficient divided by P. So remember, we take the natural log derivative, it becomes 1 over plus. Now watch what's going to happen, okay, over here. So when I do this, right, I've got my coefficient n minus the sum of x sub I. Okay, I have to take the derivatives. This becomes 1 minus P. And then my chain rule says take the derivative of what's inside. So I need to now multiply that by a -1, okay, because I'm doing the chain rule from what's inside here. And now this I need to set equal to 0 and then solve for p. Solve for the p-value, that's going to do it. So let's do some now algebra. Okay, so now, right, I'm going to set these up. So this is the sum of x sub I over p. I'm going to, this is a negative. I'm going to bring that, add it to both sides. So I get n minus the sum of x sub I over 1 minus p. I can, cross multiply. So I get 1 minus p of x sub I equals p times n minus sum of x sub I, right? All I did was cross multiply to get to this spot right here. Then I distribute things out, okay? So if I distribute things out, then I'm going to get sum of x sub I minus p sum of x sub I equals p times n minus p sum of x sub I. I've got the same term on both sides, so these are going to cancel here, okay? Now I can just solve by, right, I'm just going to divide by n, so I'm going to get my p is equal to, right, which this is our maximum likelihood estimator. It's really just the average of all of our values, right? Summing up all those values and dividing by the quantity. So p hat is maximum likelihood estimator for p, which we also call MLE, maximum likelihood estimator for p. Some books also call this p sub e for estimator. It's the same thing, but just to give you different ways of representing it. Your hardest part is setting up your maximum right? Remember, logarithmic differentiation is your best bet for the tools on how you're going to separate out all these products. Okay, and then distributing all your terms, taking the derivative, setting it equal to 0, solving for the estimate, the thing that you're looking for. Okay. That's a lot of math, but it's good. Okay. Right, and then this gives us our maximum likelihood estimator for it. Right, I think I'm going to stop here. We have some more examples to work through, but they're fairly long, and we'll go over time. So we'll continue with those tomorrow. It probably wouldn't take us, more than like 15 minutes or so to go through the rest of the examples. And then tomorrow we'll also start 5.3, but 5.3 won't be on the exam, okay? But I want to, move into 5.3 so that we don't fall behind in terms of things, okay? And then if you guys want to come to office hours and ask me questions, you should have enough information now about 5.2 to at least start on the homeworks for 5.2. That'll help you, start taking a look at that. So you're welcome to come to office hours and ask me questions about homeworks for this set from last week. Our test is not cumulative for the whole semester. It's just from our last exam. So we'll include things that we had our quiz on just most recently. Okay. All right, you guys. Have a great day. Bye-bye.
At the beginning of the year, Emperor Lemon made pretty much a documentary about the history of Hunger Books, but not just Hunger Books, but